This is an AS-D2 question on flows in networks. Figure 1 models the flow of fluid through a system of pipes from a source S to a sink T. The weights on the arc show the capacities of the corresponding pipes in litres per minute. Two cuts C1 and C2 are shown. So let's cut C1, let's cut C2, and a source here and a sink here. Part A, what we need to do is to find a capacity of, first of all, in part 1, cut C1. Okay, so what we need to consider is the capacities of the arcs flowing into that cut, and I'll just highlight them so you can see them. So we've got 40, we've got 100 flowing into the cut, and we've also got 30 here. So we want the sum of those, so 40 plus 100 plus 30, so that gives us a capacity of 170. Then we need to do the same for cut 2, C2, so we'll get rid of these here, and again we look at the capacities of the arcs flowing into that cut, so we've got 65, 10, 15 here, and 25 and 30. You do not include the capacities of the cuts that are flowing into the cut, so we don't include the 30, so we need to add those up. So that's 65 plus 10 plus 15 plus 25 plus 30, so that gives a total of 145. So we'll just highlight those. Okay, part B down here, using only the capacities of cut C1 and C2, state what can be deduced about the maximum possible flow through the system. So based on the value of these two cuts, the maximum flow cannot be any more than 145, the minimum value of these two. So the maximum possible flow based on C1 and C2 can be no more than 145, so I guess we would write that as less than or equal to 145. Part C on diagram 1 in the answer book, well, I've got that diagram down here. Show how a flow of 120 litres per minute from S to T can be achieved. You do not need to apply the labelling procedure to find this flow. So it's basically just looking at our capacitated network here and using that to help us find this flow. Now, because we're looking for a flow of 120, that means I need to have 120 flowing in and 120 flowing out. So from S to B, I've got a maximum capacity of 30 or 130, so I can have 120 there going in. So I've got to have 120 going in. Right now, the 120 is going to get split two ways. I've got a maximum of 40 here and a maximum of 60 here and a maximum of 100 here. Now we need to look along the network to see if we've got any restrictions. So although this has got a flow of 60, a capacity of 60, I'm limited to a maximum of 30 at this point here. So I'm going to put 30 on arc BC, which means the arc CF is going to be at capacity, so we'll put 30 there. And the same with this sort of arc here, so I've got a maximum flow of 40 here, but I can go up to 65, so I'm limited really from A to D by a maximum of 40, so I'll put that in 40 there, and then A to D is going to be 40, so that gives me a sum of 70 so far. So I need another 50, which I can do along arc BE because I've got a maximum capacity of 50 on there, and I've got these other arcs here which give me a sum of 50, so it is possible now to put 50 on this arc here, B to E. Now let's continue from this 50 here. For example, I can take 10 of that 50 and put it along arc ED, So put 10 there. Now that means that flowing out of D, I'm going to have a capacity or a flow of 50. That means that I also need to use the full capacity of ET and EF, the 25 and the 15, so that I get the full flow of 50 out from E. So 15 here and 25 here. If I move down to the bottom here, F to T, so I've got a flow of 25, flow of 25 and 30 going to F. So F to T is going to be 55. That's fine because I've got a capacity of 85. So I'll put 55 here. No backflow here, not needed. And I just want to check that I've got a flow of 120 going out. So 50 plus 15 is 65. 65 plus 55, that gives me 120. So that's part C. Okay, part D, what we need to do is to prove that 120 litres per minute is the maximum possible flow through the system. Now to do this, we're going to use the maximum flow minimum cut theorem. So we need to find the minimum cut through this capacitated directed network, and a minimum cut needs to pass through saturated arcs from S to T or empty arcs from T to S. So I'm going to label all or highlight all of the saturated arcs. So I've got BA is saturated because you can see it's at its full capacity. CF is saturated as well. EF is saturated. As you can see, it's up to 25. ET, saturated. ED, saturated. I think that's it in terms of saturated arcs. So those are all of the saturated cuts from S to T. Now there is an empty cut that goes from T to S, and that is this one here, which corresponds to this arc here. So that's empty going backwards. So what I need to do is to find a cut that goes through those arcs. Okay, now it doesn't need to go through all of them, but it must pass through arcs which are at capacity or empty if we're going backwards. And I think I've got one here. So if I just draw this, so it's passing through these arcs here. Okay, so I've now got this cut. So we have a minimum cut passing through these following arcs. So BA is the first one, and then from BA it crosses through ED. Then from ED it passes through ET. Then from there it passes through FE, and then it passes through the arc again but in the other direction, so I'll label that as EF. And then from EF it passes through CF. Now we need to find the capacity of this cut, and that's going to be just the sum of the flows, so 40 plus 10 plus 15 plus 0 plus 25 plus 30, which is equal to 120. So we say by the minimum cut maximum flow theorem, so we must state the theorem that we're using, the maximum flow is 120. Okay, a new pipe is planned from S to A. Let the capacity of this pipe be X litres per minute. Part E, find in terms of X, where necessary, the maximum possible flow through the new system. So let me draw on this new pipe, S to A, and this has a capacity of X. Now, if I extended the cut, which I did in part D, I can get it to pass through X. So I can have a minimum cut go through here, assuming that I put X up to capacity. So let's say that it's saturated. So in that case, the maximum flow would be the 120 that I got before plus X. So 120 plus X if X is saturated. And that would give the maximum flow in terms of X. Now, we do have a restriction as to how much X can flow, and that's 25, because if we look at vertex A, we've already got 40 flowing into it. We can only have a maximum of 65 flowing out. So the limit we have on X is going to be a capacity of 25. Now we want it to be at capacity, so actually we want X equal to 25, which would then give a new maximum flow of 120 plus the 25, which would give us 145 liters per minute.